Hi, this is Dr. Stephen Jones. We're going to be looking at Project Management, Chapter 11. So, one of the first things that we need to look at is a couple of the major processes or means of making decisions based on project management theories. That would be the PERT, or Program Evaluation and Review Technique, and the CPM, or Critical Path Method techniques. And they are not the same thing, but they are related in that they both use processes based on length of certain kinds of activities and how to determine which processes are the best to keep control of operations. It's not a decision as to whether or not a certain thing should happen, but or like a project should be undertaken, although I guess in retrospect it could be. But that's not the idea behind it. The idea here is to keep control of a project as opposed to decide which project to undertake. So if you're looking at PERT CPM, the definition of the project, again, is your first task. Make sure that you understand exactly what's going to happen, along with the activities or tasks that need to occur. Find a way to graphically represent the network of the activities, and that's really not too hard, at least for the simple types of networks that we're looking at. Obviously, if you're looking at something much more complex, you might find yourself with a diagram that would look a bit on the spider web-ish side, but outside of that, it's not generally too difficult. And then using everything else that you have generated in there, you find a critical path through that network so that you'll know where, if something breaks down or there's a bottleneck somehow, you'll be able to correct that and perhaps put some extra watch on those areas to keep processes moving slowly, and therefore try to do a better job of pre-preparation and then monitoring and completion of any project out there. Now, PERT itself will be asking a series of questions here, about 7 questions. When is any one project going to be completed, and what are the activities and their lengths and so on like that that are part of this project? If there are not critical activities, in other words, things that it's easy to figure that you could delay or reroute some activities, then which ones are those? Pay attention to your times and to any dates that are scheduled so that you meet all of the objectives that you have. Use a cost factor to see that you are staying on budget, and then find ways to potentially move things forward a little bit faster. And so we actually have means of doing all of those things within both of these processes. So let's take an example that's going to go throughout both this lecture and the next one, the General Foundry example. And if you were to look at this example, the basics are that there's a foundry that is trying to avoid fines or other costs associated with air pollution, and so they have decided to create a filter system that has some rather complex things that have to occur, and it's got about 8 different activities that have to take place with for the completion of this project. As a result of that, they want to be sure that they can get this done on time so that they don't get slapped with any fines out there. Now, these are the activities. They're shown in the text. They are shown in there, and some things are critical for you to see straight off. One, these two, A and B, are ones that do not have any predecessor activities. That means when they start, they start. And as a result, A does not depend on B and B does not depend on A. So 2 separate teams could be working on this. Now, for C to occur, A had to have occurred. So C cannot occur until A has already been completed, just like D cannot occur until B has been completed. So they're in a line of activities that go together, A and C and B and D. Then E and F both require C, and G requires that both D and E have occurred, H that F and G have occurred. And you might think, wow, that's a puzzle. How in the world are we going to figure out how that's supposed to occur? Well, you need a graphical representation, and that's what this is. So if you notice, once you've started, you can work on A and you can work on B, and B leads directly to C. Pardon me, A leads directly to C and B leads directly to D, and C leads to both E and F. And once E is done and D is done, then G can also be undertaken. H, on the other hand, needs both F and G to have occurred, and then you finish. So you can see where the flow of activities have to go. But how do you know which one is the critical path? In other words, which one, if something were to break down, you would find yourself in, a boggle out there. Well, that takes a look at activity times, because we have not looked at the activity times, just at the logical flow of activities at the moment. So, critical path method and PERT differ in this relatively important way. Critical path method says here is the length of time that activity is going to take place, while PERT says there are multiple possibilities for times here. What is the most likely time? And also we would take a look at what is a pessimistic or an optimistic look at it. So as a result of that, with PERT, you're going to look at 3 different times, but you don't weight those 3 times the same. You in fact weight the most likely time with PERT. You weight it 4 times, and then once for each the optimistic and pessimistic, and then you divide the entire sum by 6. So you're more heavily weighting the most likely time, but you do take into account the pessimistic and the optimistic. Now, truth be told, because so much weight is on the most likely time, which is also the time that CPM would actually have put down, you're probably going to have a fairly close definition of activity times for both methods, because you are using essentially the CPM time as the most common time, but there are some alterations there for the optimistic and pessimistic. Then you can also take a look at the variance. That helps you to understand whether or not that activity happens to have if it's got a small variance, then optimistic and pessimistic times are essentially very close to the critical of the most likely time. And if there's a huge variance, then there's a major difference between optimistic and pessimistic, and you'd have to adjust for that as well. So this table right here shows us what you see in the text, an idea of what optimistic, most likely, and pessimistic for each activity could be. Then you calculate the expected time and the variance. You notice that the expected time for the whole process, if you sum up all of the times, would be 25. But that is not the length of time from start of a project to the end of a project. That is the compilation of all the times for all the activities within the project. Actually, from start to finish, the only way that 25 would be the actual time from start to finish would be if A was your first activity, followed by B, followed by C, followed by D, E, F, G, and then H. So if it was linearly linked like that, that you had to do A before B, B before C, C before D, D before E, then 25 would be the actual length of time for the project. But because we have A before C, B before D, and then E, F, and G dependent upon each other and other strains, then you don't have 25 weeks from start to finish. It's going to be shorter than that because some things are going along at the same time as others. A and B are going along at the same time, C and D are going along at the same time, etc. So we put some activity times into that diagram that we had before, and that helps us to see a little bit better what our critical paths could be. Now, if you're going to have a completion time out there for this path, you have to also understand that the critical path is going to be that path that is the longest time from start to finish. So which of these is there essentially no slack in? And we'll actually calculate slack here in just a little bit. So you take a look at the earliest time to start, the earliest finish time, latest start, latest finish time for each activity so that you can see if there is some level of slack out there, where might that slack be. And now you have begun the early start and earliest finish times for each activity. You'll notice that, say, A takes place, A is a 2-week activity, and it starts when the whole project starts, and it has its earliest finish as being the second week. And B does the same thing. It is 3 weeks long, and its earliest start is 0, so that it would end at 3 weeks. D couldn't start before the B is done, which means it needs to start at the end of the 3rd week, taking 4 weeks time and ending at the end of the 7th week. C couldn't start before the 2nd week when A is done, taking 2 more weeks, so it would be 4 weeks. And that's what those numbers all mean. If there's slack, it's going to be slack because you have the ability to start a project a little bit later and therefore end that project a little bit later, because there's some room. Take a look here, just looking at the first 2 activities, not looking at what the actual critical path is. First 2 activities would appear that it takes you 4 weeks to get activities A and C completed. It takes you 7 weeks to get B and D completed. And so just looking at that, if you didn't know anything else about this model, you would say, well, darn, then maybe you could wait for a couple of weeks on A and C, because there's no problem here. They're going to take a little long, they'd take less time to complete than B and D do. But that would not be the case. A, C, E, G, and H have no slack time, because if you take a look at the process here, C leads to E and F and then to G. So before G can start, E has to start. And that means that A to C is 2 weeks, C to E is another 2 weeks, or 4 weeks in total. E then is another 4 weeks, or it takes 8 weeks before G can start, whereas B and D only take 7 weeks. So while A and C took only 4 weeks, you then have to add the E in there, the 4 weeks for E, and that makes it the critical path, because you could delay B a week, or B or D a week, and still make G start on time at the 8th week. So 15 weeks is our critical path time once you add all those numbers up. You also have the ability to have late start and finish times added to this process, so that you can see where the slack can occur and how much slack can occur at any one point. Notice that slack for F is 6 weeks, and B and D is 1 week, but the rest of the process there is no slack. So you can only find a minimum amount of slack within this model right here. Finally, to sum up this part of the lecture, the graphical representation shows the shaded boxes that are on the critical path, and you see where B, D, and F have some level of slack time in there, and they will not delay the entire objective. Okay, go to part 2.